Hello and welcome to the course of Network Security. We are in lecture number 3. In today's lecture, I will talk about some security design principles which were proposed in 1975 and still they are useful. Here is a brief roadmap for today's presentation. These are the 8 fundamental security design principles which need to be accommodated in each and every system, protocol, algorithm solution that is designed for addressing the security needs. Let us start. Our first basic goal of security or principle of security design is known as economy of mechanism. However, before going to into the details of economy of mechanism, let me briefly tell you why we need these fundamental security design principles. Actually, beside from years of research and development, it has not been possible to develop security design and implementation or solution technique that will systematically exclude all the security flaws from a system, or you can say that it will prevent all the unauthorized actions or all the attacks that have been performed on the network. That is not possible. So, in the absence of such a foolproof technique, it is useful to have a set of widely agreed design principles which will guide us in the development of protection mechanism or to make our network or information secure. For that purpose, the National Center of Academic Excellence in Information Assurance, which is jointly operated by or supported by the US National Security Agency and the Homeland Security Agency, they list these fundamental security design principles. To make things simple, these fundamental security design principles are required to be part of any system that we are going to design for making our information, for making our computer, for making our network a secure place. In these principles, the first principle is known as economy of mechanism. What does it mean? Actually, the economy of mechanism means the design of security layer should be as simple and small as possible. And there is an engineering design principle which is known as case, which stand for keep it simple, stupid, or there are alternative versions available as well. But the principle is that we need to design the security solution as simple and as small as possible. A relatively simple, relatively small design is easier to test and they are easy to verify thoroughly. If you have a complex design, then there are many more opportunities for an adversary to discover weaknesses. Okay, maybe you do not agree with this point, but that is a fact. The more complex the mechanism is, the more likely it is to process exploitable flaws in the system. Simple mechanisms tend to have fewer exploitable flaws and require less maintenance and less time for operation. And furthermore, because configuration management issues are simplified, so updating or replacing a simple mechanism become a less intensive process. So in practice, this design goal is most difficult to be achieved. Why? Because there is a constant demand for new features in both hardware and software, which actually complicate the security design task. The best that can be done is to keep this principle in mind during system design and try to eliminate unnecessary complexity. But again, this is the most difficult design principle, which we can actually achieve because the things are getting more and more complex. So you need the solutions to be complex as well, but still we need to keep them simple. So you need a balance between these two. You need to address the security needs of the system, but on the other hand, you have to keep the things as simple as possible. Okay. Our second security design principle is known as fail-safe defaults. Literally speaking, fail-safe means having no chance of failure. As you give attention, these are two words, fail and safe, mean no failure or no chance of failure. That is literally speaking. But a fail safe is actually a design feature, or you can say a design practice that, in the event of a specific type of failure, inherently respond in a way that will cause minimum or in some cases no harm to other component. What does it mean? It means that if one component is affected by some malware, for example, other components will not be affected from that from that malware. If any device or process or system fails for whatever reason, it will go to the safe outcome. This is another way that we can define fail safe. If something goes happen, you have to find the safe outcome, the safe way from that. For example, automated doors, elevators, car windshields, or process safety equipments, electronic circuits, breakers, circuit breakers, etc. All these things are designed by keeping in mind the fail safe default. For example, if a short circuit happens in your home, then the light, all the electricity power system will go to switch off by default. Okay, these have been because why it happened, because many incident, or you can say accident, happen in the past where, for example, autonomic or atomic doors of the rail car or even an elevator door would injure people while closing. But now it is mandatory for the designer to design the system in such a way that whatever reason these doors cannot close, they need to go back to the open position. And that is the fail safe default. Okay, so this principle means that the default situation is lack of access, and the protection scheme identified conditions under which access is permitted. What does it mean? That is the third way of defining the fail-safe default, which means that you have to design the system in such a way that it will restrict accesses to the system by default. And if somebody need permission to access the system, then permission must be granted on request. And this principle requires that the default access to an object is none. Mean by default you are not able to access something, access of service. Whenever access or privileges or some security related attribute is not explicitly granted, it should be denied by default. And moreover, if the subject is unable to complete its action or task, then it should undo those changes that it made into the security state of the system before it terminates. So the third principle, to keep it simple, means that default action of any security system is to deny. And you can also say default deny principle. Means by default nobody is able to access the services. If somebody want to access a service, he or she need to make a request. Based on privileges, you will then assign or deny the request or request to the service to avail the service. Okay, so to put it in summary, by default all accesses should be restricted to the system or to the service. Okay, our third design principle is known as complete mediation. Actually, as I just mentioned, every access to every object must be checked for authority. This is known as complete mediation. Every access to every object must be checked for authority. What does it mean? It means that every access must be checked whether it has the authority to access the object or not. Actually, this principle restricts the caching of information. You know the concept of cache? We talked about it in the physical class We discussed about it, how the organizations, the companies, the services providers, they actually use the cache, okay, for example, for advertisement purposes or to keep data about the customers. And this actually leads, the concept of cache lead to simpler implementation of mechanism. Every time that someone tries to access an object, the system should authenticate the privileges associated with that object. That is what complement mediation mean. But what happen in most system is that those privileges are cache, keep in cache for later use. It means that if you are using cache mechanism, then you are violating this principle of security design. Okay, simple is that. Why? For example, the subject privileges, how it happens or how it works. Let me give you an example. If you want to sign into Gmail account, then for the first time you sign in, it will ask you for password, username and password. But then it will ask you whether you would like, whether you will allow the browser to keep your credential for the future use or not. If you allow the system to keep the data in the cache, then next time whenever you want to enter into the system, into the to check your emails, the system will not ask you to provide the password again and again. Okay, so in this case we are actually violating the complete mediation principle. So cache, if you are using cache, you are actually violating it, and there is an example of the complete mediation. In a similar way, the operating system should also mediate all and every access to an object. System should not rely on access decisions retrieved from a cache to be on the safe side. This principle actually restricts the caching of information, to keep it simple, which often lead to simplified implementation of the mechanism. And the principle required that if access decisions are remembered in the cache, for example, for future use, then you have to give proper attention, careful consideration on how changes in authority are propagated into such local memories. So if you want that, no, I am interested in using the cache, then you have to keep in mind the careful considerations to be given on how changes in authority are propagated in such local memories in the form of cache. Okay, to fully implement complete mediation, every time a user reads a field or a record in a file or a data item in a database or something like that, the system must exercise access control. Every time you want to access something, an object, it could be a record in a file, it could be a data item in a database or something else. Then every time you want to access it, you have to, the system has to check the access control. Okay, and this is going to be a resource intensive approach if you are going to check the credential each and every time. Okay, in Unix operating system, I know that a process they try to read a file, the operating system determine if the process is allowed to read the file or not. If so, the process receive a file descriptor which allow the access. And whenever the process want to read the file, it present the file descriptor to the kernel, which is an important part of the operating system. And you know about it. What are the functionalities of a kernel? So the kernel actually allow the access. But if the owner of the file disallow the process permission to read the file after the file descriptor is issued, then the kernel still allow access, although the user has denied the future accesses. But as we are using the kernel, which has no information that the access has been denied, but still it will allow the access. And similarly, this scheme actually violates the principle of complete mediation, because second time access was not checked properly. Why? Because the cache value was used, which actually result in the denial of access being ineffective. And there is another example, but I will not go into the detail, and that is related with the DNS. For example, the DNS cache actually the functionality of the DNS is to map host name into IP addresses and vice versa. So actually it uses cache for doing so. But if an attacker is able to poison the cache by implanting records associated a bogus IP address with a name, then one host will route connections to another host incorrectly. There is another security breach. So to be on the safe side, it is important to follow this principle, which means complete mediation. And actually, in summary, it means that every access to every object must be checked for authority, and it is against the use of the cache. Our next principle is about open design, and this is very simple. Keep things open to the public. Open design means the design of a security mechanism, the design of a security solution, the design of a security protocol, the design of a security algorithm, whatever it is, it should be open rather than a secret. The design should not be a secret. The security of a mechanism of a solution should not depend on the accuracy of its design. Designer and implementers and protocol designer of a program, they must not depend on the accuracy of the details of their design and implementation to ensure security. Means it should not depend, it doesn't mean that you are going to ignore the potential attackers. Rather, we are actually trying to separate the keys and password from the design. The password, the keys, they must be protected, they must be keep safe, private. However, the design should be public. So do not mix the two things. Password, keys, they are something else, while the design of the protocol solution mechanism, there is something else. And this is very much true in the case of cryptography. Actually, we will study cryptography in the coming weeks, but there is a concept of there is a backbone of security system, by the way, because cryptography is highly mathematical subject, and companies that actually market cryptographic software to protect user data, they frequently keep the algorithm secret. Okay, and experiences has shown that such secrecy aids little, if anything, to the security of the system. That is not a good approach to keep the algorithms secret or to keep the solution, the mechanism secret, because keeping the solution will actually not strengthen the security. What happens normally in cryptography, that we try to keep the keys and passwords secret, and it doesn't mean that you are violating this principle, because the principle said that the design must be public, but here we are talking that we need to keep the keys and passwords secret, so it is against the design, but actually it is not. What does it mean? It means that the algorithm, the security mechanism, it should be public. However, the keys and passwords, they must be secret. Okay, and to be more specific, more technical, it means the encryption and decryption algorithm uh, should not be secret. If they are secret, then you are actually violating this design principle. Our next design security design principle is known as separation of privileges. In simple words, it means split the system into different pieces, and each piece must have some limited privileges. Actually, the principle focuses on the separation of privileges, states that a system should not grant permission based on a single condition. Separation of privileges means a practice in which multiple privileges attributes are required to achieve access to a restricted resources. Separation of privileges means if you want to access object A, it will require a different type of privileges. If you want to access object B, it will require a different type of privileges. A simple example is that if you want to check the amount in your bank account, then you only need to provide in the online, if you are using online a website to access your account details, then you have to provide your account number along with password. But if you want to transfer monies to someone else, or if you want to perform a transaction online, then another type of privileges is required, which means now you have to provide another secret key or password which is unique to you. Only you know about it. That is the separation of privileges. And also, a third type of security could be that beside giving the password, you will have to receive a token, a PIN code, a one time use password on your mobile number, and then you have to provide it as well in order to complete the transaction. So, what is this? This is actually the separation of the privileges. And companies are following this principle very much in today's world. Okay, so a protection mechanism that actually requires two keys or more than two keys to unlock or to perform the operation. Actually, it is more robust and flexible than using a single password to access each and everything with a single key. There is not more sophisticated approach. Okay. Our next design principle is least privileges, also related with the privileges. Least privileges, as the name indicate, every program and every user of the system should operate using the least set of privileges which are necessary to complete the job, the task. Least privileges mean that the minimum number of privileges that can be assigned to a user to perform the task. And this principle actually limits the damages that can result from an accidental, intentional, or unintentional event that could happen. It also reduces the number of potential interactions among privileges program to the minimum for correct operation. If, for example, a question related to misuse of a system or of a privileges arise, then the number of program that must be audited is minimized. Okay. So a good example to understand the least privileges is the use of the principle in role-based access control. If somebody is working as a network administrator, he better know about this concept, role-based access control. And this is actually the least privileges, something related with the least privileges principle. What we do here, actually, the system security policies can be identified and defined the various roles of users. For example, if somebody job is just to enter the data into the system, then we need different type of privileges for that person. If the role of the person is to analyze the data, then he or she need different type of privileges. If the person is more administrative, is on more administrative level post, then he would obviously need more privileges. But in all the cases, we have to provide the least privileges possible to each and every category of the user. Each role is assigned only those permissions which are needed to perform day-to-day tasks. And each permission actually specifies a permitted access to a particular resource. For example, you are able only to read the file, another person is able to write the file or to edit the file as well, another person is able to delete the file as well, and things like that. These are example of role-based access control. More generally, any access control system should allow each user only the privileges that are authorized for that user. If you want to do something beyond those privileges, that would not be accepted by the system. Okay. And our next design principle is again something related with the mechanism, but this time we are focusing on the common mechanism, least common mechanism. Mechanism that are used to access resources. They should be keep as less as possible. And common mean they should not be shared among different users. Actually, this principle is restrictive because it limits the sharing of resources. Sharing resources actually provides a channel, communication medium, along which information can be transmitted, can be sent, can be communicated. And every shared mechanism actually represents a potential information path between users, and it must be designed with great care to be sure that it does not unintentionally compromise the security. So, what does it mean in simple words? It means that sharing should be minimum as possible. Sometime, if the operating system provides support for virtual machines, it is a concept which is very much in cloud computing, virtual machines or virtualization. So the operating system will enforce these privileges automatically up to some degree. Actually, this principle will help reduce the number of unintended communication paths, and it will actually reduce the amount of hardware and software on which all user depends. Uh, to make things simple, let me give you an example. A website actually which provides electronic commerce services for a major company. There could be attackers who want to attack this electronic commerce website for their beneficial benefits. What they can do, they can actually flood the website with messages in order to slow down the website or completely let down the website. What will happen if the website is down or slow? The legitimate customers, they will not be able to access the website anymore. And this will result in business losses. Why it happened? Because they shared the details on the internet with the attackers. So actually they get this clue from shared resources on the internet. We will study different types of attack in the coming lectures, but in summary, let us conclude this seventh security principle. It means that the shared resources should be kept as minimum as possible to be on the safe side. And lastly, the eighth principle is psychological acceptability by the customers. Actually, this principle is directly related with the humans, not with the machines. With the psychological impact, the psychological factors of the human beings. Actually, the security mechanisms should not make the resource more difficult to access. If you are not using any security mechanism, then the user are happy with the performance. But if you are using security mechanisms, the user would complain performance issues. If you are using complex algorithm for security purposes, performance will affect. Delay, for example, would be there, or many security checks could be there. So it is essential that the human interface be designed in a way that could be easy to use so that the user routinely and automatically apply the protection mechanism correctly. For example, if the security related software or security related system are too complicated to configure, to maintain, to operate, then in that case, your user will not employ the requisite security mechanism. It is a psychological effect on them. If the security mechanism hinder the usability or accessibility of resources, user will not opt to turn on the security mechanism. Psychological effect. But at the same time, programs should not impart unnecessarily information that may lead to a compromise in security. You will not do something that will let your customer happier, but they have to pay for security. Okay, if the security is compromised, then there is no way to let your customer satisfied with your services. Security must be there, but you have to keep in mind the psychological effect of the users, of the customer, of the human beings. And remember, in the last lecture we talked about a balance between security and access control. This is actually the principle which focuses on that aspect. Okay, so unnecessary security mechanism should be avoided in order to let the user enjoy best performance from the system. An example, When a user supplies the wrong password during login, then in that case the system should reject the attempt with the message stating that the login failed. Okay, look at the psychological factor here. If the system say that the password is incorrect, then what will happen? The user would know that the account name was legitimate. If the user were really an unauthorized attacker, then what will happen? He will get a clue. Okay, the username is correct. The problem is with the password. Then he or she would then know the name of an account for which he or she should try to guess the password. So your system must communicate in an efficient way with the user. It will not give clues to the attacker or unauthorized user. Actually, in practice, the principle of psychological acceptability is interpreted to mean that the security mechanism may add some extra burden, but that burden must be kept minimum and reasonable on the other side. Okay. Beside from these 8 basic or fundamental security design principles, we also have some other design principles that were introduced into the model, and they are like isolation. Isolation mean that public access system should be isolated from critical resources like data, processes, etc. in order to prevent attacks on the system. Or isolation also mean that the processes and files of individual users, they should be isolated from one another except where it is explicitly desired, like in case of virtualization. And it also means, isolation also means that the security mechanism should be isolated from the access mechanism. Okay. And also we have encapsulation, uh, but we will not go into the further details of these components. What is important is the modularity and layering. And actually layering is much more important, which refers to the use of multiple overlapping protection approaches, addressing the people, the technology, the operational aspect of the information systems. And also we have the least astonishment, which means the program, or you can say the user interface, should always respond in the way that is least likely to astonish the user. Astonish means to surprise the user, to amaze the user. For example, the mechanism for authorization should be transparent enough to a user that the user has a good intuitive understanding of how the security goals may to the provided security mechanism and things like that. But we will not go into further details of these principles. This was about some fundamental security design principles. In the next lecture, we will be talking about OSI security architecture, like security attacks, security mechanism, and security services. Till then, goodbye.